Hello friends, this is a compilation video of all of my lectures on the topic of work, energy, and power, potential energy graphs for my AP Physics C class. Um, in the description below, you can find the links to all the notes, the note packets that I'm teaching from, and you can find links to the original lectures individually if you want to study that way. So don't forget to like and subscribe and share, and good luck learning about energy.
Okay, welcome to Unit 3. This is the unit on energy and work and power and all that kind of stuff. A lot of this is going to be reviewed, but again, we're going to be introducing some calculus. So let's get to work. Definitions, this is all review. Actually, everything in 7.1 to 7.6 should be review. We're reintroducing dot product, but again, so definitions, what energy is. For our purposes, it's the ability to do work. It's actually something that's really mysterious. You talk to scientists, physicists, like what exactly is energy? Very hard to say. But for our purposes, it's the ability to do work. We've got kinetic energy, potential energy, and work. The thing about work that's interesting is that work can be positive or negative. These are all scalar quantities. But work can be positive or negative because we can be adding to or taking energy away from a system. Potential energy can be negative gravitational potential energy, because when we calculate gravitational potential energy this way, mgh, what we're doing is we're referring to some standard, right? What's the potential energy from this point? It's not like absolute potential energy, it's relative potential energy. And kinetic energy is 1/2 mv squared, which you should be aware of. The change in kinetic energy is kf minus ki, and that is often equal to the work. We're going to have a more expanded version of this conservation of energy and the way that it's related to work. But for now, we'll do that. So work, if I push on a wall, do I do work? No. Is work a vector or scalar? It's a scalar, but I can't have negative work, right? And work done by a constant force, for now, is going to be FD cosine theta. What is this? It's a dot product. And so as a result, if the angle between the force and the angle between them is important. If the angle is less than 90 degrees, then you're doing positive work. If the angle is greater than 90 degrees, then the work is negative. Right? What this means here, if it's less than 90 degrees, that means you're pushing generally in the same direction as the velocity, and so you're adding to the velocity, right? You're adding to the energy of the object. But if the angle is greater than 90 degrees, that means you're pushing in the opposite direction of the motion. And so you're taking energy away. So negative work, you're losing energy out of the system. You can think of work as the change in energy. Right? If the energy changes into or out of a system, that had to be done by work, by some external force. If the angle is equal to 90 degrees, then the work done is 0. Remember the dot product, scalar product, right? A dot B is AB cosine of theta, right? Or it's also equal to AX times BX plus AY plus BY plus AZ times BZ. I dot I is 1, and that's true for the other one. J dot J is 1, K dot K, and all the other ones, I dot J, J dot K, K dot I, are all 0. The next thing with these two spies that are there, the work a force does on an object depends on the angle between the force. So just some examples. The work done by the normal force is 0 because the normal force is pushing up, but the displacement is sideways. The work done by gravity is 0. The work done by the spies is FD, right, cosine theta, or FD cosine 40. If friction was present, then the work that friction would do would be the force of friction times d times cosine of 180. Right? Why is that? Because the friction is taking energy out of the system. If the friction wasn't there, this thing would just be getting a lot faster. But it's not getting up to that speed because friction is there. It's removing the energy over time. So in general, normal force does 0 work. Friction force in general does negative work. Gravitational force does negative work if the displacement is up, and it does positive work, right? Gravitational force then does positive work when the displacement is down. Okay, so here's an example. Right, we're given a force and a displacement. It says calculate the work done by the force. And so this is going to be F dot D will be 2I plus 3J newtons times 4I meters. So 2I and 4I gives me 8. And then 3 times I've got, it's just 0 there. So this is just 8 joules is the answer. And now we want to know what is the angle between F and D. And so we've got two ways we can do this. Right? Remember, FD is also equal to FD cosine of theta. And so I could do this where I take the magnitudes and this. Well, I know this is equal to this, so cosine of theta could be F dot D over the product of the magnitudes. And I already know this, but then the product of the magnitudes, I have to do square root of 2 squared plus 3 squared times 4 squared. So that, I mean, I could do that, but let's not forget some basic tools that we have. This is in the I direction, right? So this is the displacement. This is like this. It's over 2 and up 3, right? Here's 2, this is 3. Can I find this angle pretty easily? Because isn't this angle, or no, sorry, this would be 3. Isn't this angle just the inverse cosine of, or inverse tangent of 3 over 2? Right? Why can't I do that? So it should, I think it comes out to 56.3 degrees. You just do inverse tan of opposite over adjacent. You can do this, but don't forget simpler things that work. It's easy to be so educated that you become stupid. Don't let that happen. Example 2, work done by a constant force. So we've got a person pulling a child in a sled. This is a common kind of problem that you've seen before. Okay, and so it says, how much work does the man do pulling the sled? So let's do the free body diagrams here and figure all this out. All right, so we've got to do some work here to figure out what this force is so that I can then take the multiply this by the displacement. So Fg, this is 45 times G. Did I use G here? What did I use? I used 9.8. But let's just say this is, all right, Fg. So this is Fa. So this is Fa cosine theta. This is Fa sine theta. So I'm going to get rid of this one now. And I know that Fa cosine theta is equal to mu Fn, which is this. Okay. And then Fa Fn is going to be equal to Fg minus Fa sine theta. Right. And so what we can do is we can substitute, I can divide this by mu. All right, what do I want to do here? If I'm solving for Fa, I can solve both things for Fn. So this is going to be Fa cosine theta over mu is Fn. So now I've got Fa cosine theta over mu equals Fg minus Fa sine of theta. So I have Fa cosine theta equals mu Fg minus mu Fa sine of theta. I'm going to go up here now. Bring the FA's together on the same side. So Fa cosine theta plus mu Fa sine theta equals mu Fg. This is getting messy. So now I factor out FA, sorry, and this is then cosine theta plus mu sine theta equals mu FG. So FA is equal to mu FG over cosine theta plus mu sine theta. When you plug in all the numbers, 0.1, and this is 45 times 9.8, this is 30.1, 30, you should get something like 48.1 newtons. So that's what FA is. So now we want to know how much work does the man do pulling the sled. So that's just going to be this, FA cosine theta times the distance that it goes, and we say that it has a displacement of 5 meters, times, I'll just write d. So this is 4.81 times cosine of 30 times 5, and I think you should get 208 joules. B asks about how much work does friction do? Notice this, that he's pulling at a constant velocity. So even all this work, he hasn't increased the energy at all. It's still going at the same speed. There's been no change in the kinetic energy. And so that means that friction has done this same amount of work. And so negative 208 joules, right, the same magnitude of work. See, it says, what is the net force in the sled? 0 newtons. What about D, the net work done? 0 newtons, or 0 joules. Why is there zero net work done? This is the force of friction. This is the work done by friction, work done by the man. Those add up to 0. Also, we can see there's no change in the kinetic energy, and because E, the change in the kinetic energy. Okay, now this is review as well. Since work is force times displacement, we can look at this as the area under a graph. Now, in the next thing, for 7.8, 7.9, this is where this is really going to get jacked up a lot. This is going to go to the next level. I'm going to introduce some new calculus later on. But for now, we're just recognizing that force times displacement gives me work done. This should all be review. And so I'm just going to put the answers up to example 3 and work along with this. All you're doing is finding the area under the graph, and that'll tell you how much work was done in that time. Okay, so you should be able to do this. It's just the area of a triangle, area of a rectangle, area of a triangle, and then the total, add them up. All right, so let's try example 4. Okay, so for this section, right, 8 joules, 12. This is the amounts of work done in each of these sections. I can have negative work because I can have, I'm taking energy away from the system, and here that shows up as negative area. I'm below the x-axis or the d-axis on the graph. And so I have negative work. That means I'm taking energy away from the system. So the total work done, the total energy added to this system, whatever it is 12 joules. Now for example 5, the key thing here is keep in mind this is acceleration versus displacement. How does that work? Well, force and displacement is the area that gives us the work done. So if it's acceleration, well, how do we get force from acceleration? Just multiply by the mass. You can do this 2 ways. You can take the numbers as they are, just take that whole axis and multiply it by the mass, or you can get the whole area and then multiply by the mass at the end. Okay, either way, let's find out what the answers are going to be. So that's it for that. Now we're going to, so this is the graphical method. The analytical method is going to involve some calculus. Okay. And so, imagine that you're not given a graph, you're given a function. And let's say that the function looks something like this. By the way, we're on now to 7.8 and 7.9. We're skipping 7.7 for now. Let's say the graph looks like this. Here's force, here's displacement. Okay, how do we do that? We don't have a formula right now for finding the area under this graph. Well, one thing we can do is approximate. and maybe you've done this. If I can draw rectangles kind of like this, and then I find the area of the rectangles, that'll work, right? But what if, how many rectangles do I draw? And how wide are the rectangles, that kind of thing. It becomes apparent pretty quickly that the smaller, the thinner I make these rectangles, the better the approximation is going to be. So what if, I had something like this, where I could, I have this rectangle, all these rectangles, and this is good. This is going to give me a good approximation, but couldn't it get even better? Couldn't I make these even smaller somehow? And what is this? This is force, right? Force, which is a function of the displacement. And this right here is delta x. What I want to do is, in order to get the best approximation, is I want to take the limit of force times delta x, but as delta x gets closer and closer to 0. Right. So I'm looking at a limit, and this is covering all of these things. By the way, all these slides. I'm just sort of talking you through it. This idea of approximation and getting the area. What if we make it really small? So what we're going to end up with now is definite integrals. And in physics, 90% of the time we're going to do definite integrals. In calculus, you'll do indefinite integrals, sometimes in here as well. But we're going to get into some complicated stuff, but it's going to be very specific, and it's the same kind of complicated thing over and over again. And so what are we talking about here? It turns out that if this function, if f is, let's say, d squared, then the area under this graph is just the antiderivative. Taking the derivative gives you the slope. Taking the antiderivative actually gives you the area. So when we're taking the antiderivative, we're thinking backwards. I'm saying, what function, when I take the derivative, would give me this? And so I can imagine, okay, I've got something. Well, when I take the derivative, the exponent's coming down, right? And so then this we have to have started off with d cubed. But if I take the derivative of this, I get 3d cubed. Right? So, and I don't have anything here. So that means this must have had a 1/3 in front. If I take the derivative of this, I get that. And again, here's the point. Taking the area under the graph, and I'm not going through the proof or anything. You're taking my word for it. We'll get to the proof thing in calculus. That taking the area under this graph is like doing a backwards derivative. We call it finding the antiderivative. And we're going to set, and what we do is we set limits to this. Okay. So for monomials, right, if f of x is in this kind of form, d squared, then what I'm doing is I'm adding 1 to this, which you can see there, and I'm dividing by whatever this new exponent is. Okay? What's up? Okay, now I got kicked out of the room, and so here I am back in the office. Here we go. So let's continue. Okay. One thing to think about here is that why can't, looking at the instructions here, why can't n be -1? So why can't I have x to the -1? This would be 1 over x. And so then, or rather, sorry. So then when I'm adding 1, then I'd be ending up with, on the bottom of that fraction there, 1 over n plus 1. So that means that I can't just use my normal rules to anti-differentiate this. All right, there's going to be something else that we do when we have this. So now taking definite integrals. So I'm looking for an integral over a definite period of time. And so what all this looks like, so let's take the example that's here. So we're looking for the integral from 1 to 5 of x squared dx. All right, what does this mean? The dx here is referring to the thing that I'm integrating with respect to. You know what, let me write this again. So what is this giving us the area of? Well, nothing in particular. You remember this dx, if I had some function and I'm taking the derivative, I would have like dy dx, something like that. So dx is like a little piece. And in the graph, x squared is giving me the height, and dx is that tiny width that's here. So delta x, which is now dx, as delta x approaches 0. So this is really what I'm doing is I'm adding up. So instead of a sigma like this, I'm stretching out an s, so a summation. I'm doing a summation from 1 to 5 of all of these heights at these various locations times these tiny, tiny little widths. That's what this means. All right. And so what I do is I anti-differentiate, and I end up with 1/3 x cubed from 1 to 5. And so now I plug in these two, and I subtract. So this is 1/3 5 to the third minus 1/3 1 to the third. That's the idea, right? I'm plugging in the final minus the function of the initial. And so this ends up being 1/3 of 124. Okay, and that doesn't come out evenly, so I'm just going to leave that like that. Let's take a look at example 2. Well, it's a little different. So this is now taking the integral from 1 to 5 of 4x squared dx. Okay. Friend saying hi. And then, so this now is going to become 4/3 x cubed, right? If you're getting confused going from here to here, just think, what is the antiderivative? The derivative of what would give me this? Right? And I'm going from 1 to 5. So this now is 4/3. Let me do this. 5 cubed minus 4/3 times 1 cubed. By the way, when you're doing this, anything that's out front here, you can sort of leave in the front, because those are things that are going to be common factors. Right? You can factor those out. So this is the same thing. So this ends up being 4/3 times 124 also, or 496 over 3. Okay. So now, what if the function is equal to 1? 1 dx from, let's say, 1 to 5. Well, what does this look like? Right? This is a function. What's the function? The function is just a line at height 1. And so from going from 1 to 5, here's 1, here's 5. This should end up just being, like 4 times 1, 4. Well, the derivative of what gives me 1? Let's work this way now. The derivative of x gives me 1. And so I'm evaluating x from 1 to 5. So this is going to be 5 minus 1, and it gives me 4. It's exactly what I thought it would be. Okay, and then what if it's not 1? What if it's 3? Something like this. And we're going to do this from 1 to 6. Again, same thing. This is just a horizontal line at height 3. So the derivative of 3x would give me 3, right? The derivative of this gives me this. I'm working backwards. I know what variable to put in here because I know this. This is dx, so this is becoming an x. This is from 1 to 6. So this is 3 times 6 minus 1, or 15. All right, then if we have a polynomial, it works the exact same way. So here again from 1 to 5, I'm going to do 3x squared plus 4x dx. Okay. And now we're doing the Pledge of Allegiance, the announcements.
To the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Good morning.
Okay, and now they're doing the announcements. You might hear them in the background, but we will press on. Okay, the antiderivative of this is 3 over 3 x cubed plus, and this is going to be 4 over 2 x squared. From 1 to 5, of course, right? So these simplify, thankfully. So this is going to be 5 cubed plus 2 times 5 squared minus 1 cubed plus 2 times 1 squared. So this is going to be 125 plus 5 squared is 2550 minus, this is 1, this is 2, so minus 3. So it ends up being 172 as our answer. That's it, no units. This is math, not physics, apparently. So now we're going to do some physics in example 5. And it looks like this. We have force, the force function with respect to position, right, is 3x plus 7 newtons. How much work is done by the force between 1 and 6 meters? And so I'm taking the definite integral from 1 to 6 of this function, all right, dx. Okay, and so I take the antiderivative of this. This is going to be 3 over 2 x squared plus 7x, and this is going from 1 to 6. Good. Now I plug in. Okay, back to recording. It told me I had to stop recording because lack of disk space or something. Anyway, here's what we got. This is the solution to the problem. I think it left off where I was doing this, 1 to 6, and then I plug in 6 minus, and I evaluate this at 1, and let me make sure this is recording correctly. Good. And so then I get this answer. And I was explaining, how do I end up with joules, right? I do something here, I've got newtons, I end up with joules. What's going on? Keep in mind here that when we're taking an integral, it's like multiplying, right? I'm multiplying this by this. And so this is newtons, this is meters. And so I multiply newtons and meters and I get joules. That's what I get. So let the units help you out. When you take the derivative, that's like dividing, right? That would be newtons divided by meters because you're looking at slope. But when you're taking area, that's what taking an integral is. And you can let that help you. When you're taking a test or something and you forget, oh, for this value, do I take the derivative or do I take the integral? I forget. Let the units help. If you think to yourself, I've got newtons and I've got meters, and I want to end up with joules, I have to multiply newtons and meters to get joules. Okay, taking the derivative or taking the integral, which one gives me multiplication of these two units? And integration is what gives you multiplication. So let the units help you, and keep in mind, integration is like finding area, it's like multiplying. Derivation is finding the slope, that's like dividing. Okay? Okay. So let's take a look at this last example. Okay. Here we go. So the restoring force of a spring, and we're going to do a lot more with this later, negative 450 x. So what does this mean? Why is the negative here, by the way? Let's just talk about this for a second. If I have some spring, whatever the displacement is, like if this is the 0 and this is the position x of the block, what direction is the force? The direction of the force is in the opposite direction of the displacement, right? If I displace it this way, then the force is going to be that way. So that's what we're saying here. The force is just in the opposite direction of the displacement. Okay, having explained that, now we want to go from 0.2 to 0 meters. Right? How much work is done? Because, why do we need this now? We need this because the force is changing. It's not a constant force anymore. When we have a changing force, we've got to do this. And so this ends up becoming negative 450 x dx, right, multiplying the little the little horizontal pieces by the heights, right? This is the function. This gives me the height on the graph. And I'm going from 0.2 to 0. Okay, so this ends up just becoming negative 450 over 2 x squared. From 0.2 to 0, we like having zeros because now when I plug the 0 in, it goes away. So it's like 0 minus, and then I plug in the 0.2, so it's negative 450 over 2 times 0.2 squared, and I end up with 9 joules. That's it. Okay, and then real quick what power is, we'll get into more of this later, but power is the rate at which work is done, and it's measured in watts. You already know that. That's all review. And that's it for the first part of Chapter 7. Welcome to Section 7.7. Now we're going to discuss springs. And when we're talking about springs, we need to be careful about deciding, are we talking about the work done on a spring or the work done by a spring? Because one way or the other, it'll change the sign, positive work, negative work, that kind of thing. So looking first at the work done on a spring, whenever a spring is compressed or stretched, the work is done on the spring by some applied force, right? Now imagine if you're stretching the spring, the force and the displacement are in the same direction. So if we're looking at FD cosine theta, right, the dot product F dot D, then in that case we're going to have positive work done, right? But when you have work done on a spring, if the spring obeys Hooke's law, F equals Kx, right? And so it's positive, F equals positive Kx. However, if the force is not, so that's the force, right? F equals Kx. So to find the work done, then we have to use calculus, right? And this is a Hookean spring, by the way. If a spring obeys Hooke's law, F equals Kx, then it's called a Hookean spring. If it doesn't obey Hooke's law, then it's a non-Hookean spring. So just be careful about that. And so in this case now we've got F equals Kx. So then the work done on the spring by some applied force is going to be this. Work is the integral, right? We're adding up all the little work that's done over some distance, right? So x initial to x final. Here's our starting point, here's our ending point. So it's like this is a graph of the force, and we're adding up all the little pieces of the force over time. But what's the function that tells us the force? I'm going to substitute in here kx. So this is kx, because this is now this function. It's in terms of x dx. So this means I'm looking for the antiderivative of this with respect to x, and then plugging in these things, right? So that ends up becoming 1/2 kx from xi, or 1/2 kx squared, to xi to xf. We substitute in, so it's 1/2 k xf squared minus xi squared. Notice it's just the difference of the potential energy of a spring, a Hookean spring, right, if we use kx. And so that's where that comes from, right? It all ties together. So now the work done by a spring, if you're stretching a spring, when you're stretching it, the displacement is in one direction, but the spring is pulling in the other direction. So F dot x, or F dot delta x, the force dot product with the displacement, is negative. And so then the spring is doing negative work, because the spring is pulling in the opposite direction that the displacement is going. Okay, so make sure you know what we're talking about, the work done by the spring or the work done on the spring. Okay, and so work is done by a spring as it attempts to restore its length back to the original length. So let's see, work done by the spring, we get the force of the spring is negative kx, and then all of this ends up being the same, right? Except that this is negative, means this is negative, this will be negative, and since I still have the negative in front, then the work done by the spring will be 1/2 k xi squared minus xf squared. Notice it's just the negative of that, of the one that we had before. right? And so as long as we have both of those forces there, energy is conserved because the work done by the person is the same as the negative of the work done by the spring. All right, so here's an example. Work done on a spring and work done by a spring. We have a simple harmonic oscillator, spring constant 250 newtons per meter, is compressed 0.06 meters by an applied force. We want to know what is the magnitude of the applied force required to hold the spring in this compressed condition. Okay, so let's erase the board. Get ourselves some space here. This should be simple. This is just F equals Kx. It's a Hookean spring. And so it's 250 newtons per meter times 0.06 meters. And so I'm going to get 15 newtons as the force necessary to keep it in place there. Now I want to know how much work did the applied force do compressing the spring from equilibrium to 0.03 meters. All right, so let's take a look. If we use calculus, we're going from 0 meters to 0.03 meters. F is a function of x dx. So this is 0.03. And f of x is kx. K we know is 250. So 250 x dx. So this is going to end up being 125. That's not 125. 125 x squared from 0 to 0.03. I plug in the numbers and I get, this is 0.1125 joules. Now I want to know the work done by the applied force compressing the spring from 0.03 to 0.06 meters. By the way, we're compressing this now, so the force and the displacement are in the same direction, so we're expecting the work done by the applied force to be positive, and that's what we're getting here. That's a good thing. So now we're going from 0.03 to 0.06, f of x dx. So this looks the same as this, except that now our starting point and end points are different. So 0.03 to 0.06. This turns out to be 0.3375 joules. This is more than this. Same distance covered, right? But not the same area covered. Here, this is more work. Why? Because there's more force. It's already compressed, so you have to exert a greater force now. Greater force is going to result then in more work having to be done. Now the applied force is removed, and the spring now oscillates about the equilibrium position with an amplitude of 0.06 meters. D, how much work did the spring do to return the oscillator to the equilibrium position? All right, work done by the spring. So now we're looking at negative kx, right? Or the negative of this. So D is going to be going from 0.06 to 3, or to 0, right, from the maximum amplitude back to the equilibrium position. And it's going to be negative f of x dx. And so this is the negative of what we had up here. So negative 125 x squared from 0.06 to 0. And so now this is going to be negative 125. I plug in 0 squared minus 0.06 squared. And I'm going to end up with 0.45 joules. Okay, that's interesting. Why is this positive now? Well, it's positive because the spring is now in this case, is pushing in the same direction as the displacement. If this is the spring that was compressed, the force on the spring is this way. And the displacement is also that way because the spring is restoring it back to its equilibrium position. So I'm expecting positive work, and that is what I get. All right, and then it says, if the mass of the simple harmonic oscillator is 0.5 kilograms, what is the speed of the simple harmonic oscillator as it passes through the equilibrium position? Okay. This now is conservation of energy. So for conservation of energy, I know K equals 1/2 mv squared. This is the work done by the spring. And so if that's the work done, that's going to be equal to the change in kinetic energy. So this is going to be equal to 0.45 joules. So all I'm doing is multiplying by 2 and dividing by m, and we end up with 1.3 meters per second. Okay. Okay, example 2, work done by and on a spring. We have a Hookean spring. Hookean, again, that means it obeys Hooke's law, F equals kx. And we have the mass of the block. They're connected and placed on a frictionless horizontal surface. A force of 100 newtons must be applied to compress the spring to 0.05 meters. Okay, so here's the sketch, and here's the block. It's 0.25 meters, and it says calculate the spring constant. So we know F equals kx. We're looking for k. We know the force and we know the displacement, and so k is going to be F over x. The force here is 100 newtons, and the distance is 0.05 meters. This is the same as 1 over 20, so 20 times 100 is 2,000 newtons per meter, and you can see the units right there, newtons per meter. It's Hookean, so we know that it obeys this rule, and we can apply that. How much work, or B, how much work did the applied force do compressing the spring from equilibrium to 0.05 meters? Okay, again, we can do this using calculus. We could also do this using conservation of energy, right? At zero, at the equilibrium position, it has 0 elastic potential energy, and then it has elastic potential energy of 1/2 kx squared. But again, to get used to the calculus, what are we doing? We're starting at 0, we're going to 0.05 meters. Kx dx, this is our function that tells us the force. And so we're going to end up with 1/2 kx x initial squared. Let's just do kx squared from 0 to 0.05. So this is half of 2,000 times 0.05 squared, and then it would just be minus 0. This ends up being 25 joules. Okay, so then how much work did the spring force do to return the oscillator to the equilibrium position? So now you've let go, and now it's going back. Well, the force of the spring is this way, and the displacement is also this way. So they're both in the same direction. It's going to be positive, and it's going to be the same amount of work as this. So 25 joules, right? Just like what we saw before. And then we want to know when the applied force is removed, what is the speed of the mass as it passes through the equilibrium position? Again, we know this is conservation of energy, so 1/2 mv squared is equal to the work done to get it to that point, which is, these are all 2.5 joules. Couldn't read my own writing. And so this is going to be equals 2.5 joules. Plug in the mass here, which is 0.25, and we get that V is 4.5 meters per second. So here's the tricky thing. Not all springs obey Hooke's law. Not all springs have this rule. They follow F equals kx. Some have a different function, that the force is equal to something else times x, x squared, whatever it might be. So in example 3, we have an example of a non-Hookean spring. So if the restoring force is given by this function, F equals negative 200x squared. All right, let's write that down. What work is done by an applied force that stretched the spring from equilibrium to 4 centimeters? So going from 0 to 0.04 meters. All right, so we're doing an integral, and we're looking for the work done by the applied force. So we're going to go from 0 to 0.04. We're looking at F as a function of x, dx. Now what is our force here? What's our function? 0 to 0.04. It's negative 200 x squared dx. All right, so this ends up being, when I take the integral, right, the antiderivative of this, I've got to think backwards of taking the derivative. And so this ends up being negative 200 over 3 x cubed, 0 to 0.04. Right? This would be the derivative of this, so we've got to work backwards. So this ends up now becoming 0.00427 joules. Right? And why is the negative there? So this is the force. This is the force by the spring. Since we're looking at the applied force, this would be the force in the opposite direction. So we're going to get rid of the negative, and we're going to leave it positive. So that's the first part of springs. Now we're going to look at some more springs. This is section 7.7, day 2 in the packet. Comparing FA and the force of the spring graphically. Let's take a look at it this way. Here is some spring attached to some block. Say this is 0, and this is the negative direction, this is the positive direction, right? If I look at the force, my applied force, if I move this thing this way, then it has negative position, but I have positive force, right? Or rather, right, in order for me to move it this way, oh yeah, I'm pushing in the negative direction, and the position is in the negative direction as well, right? So we're down here. And then if I'm holding the block over here, I'm having to pull this way, and then the block is also this way. So FA versus X looks like that. But the force that the spring exerts, right, as I do this, so the force of the spring in X, as I move this way, the spring is pushing that way, even though I have a negative position. And the farther I go, the greater the force of the spring. So this looks like this, right? And then as I move this way, the spring is pulling back in the negative direction. And so the spring is exerting a negative force, even though I have positive position. So that graph is going to look like that. And so we have these two different graphs, applied force and the force of the spring. It's important to keep that in mind when you're doing these problems so you get the positives and the negatives working out correctly. Now, what we're going to do is we're going to derive the effective spring constant when we have springs in parallel or in series. Just key things to keep in mind. You want to think about this. If I have two springs and I attach one and then I attach the other one, am I going to get a larger stretch or a smaller stretch from those two springs? Right? So imagine I've got two springs of the same spring constant, and I hang a weight from each of them. Right? And so there's a certain force here. What's the force? The force is just whatever the weight is from these things. So Fg is pulling down. And so that means that these springs have stretched a certain distance delta x. Right? But when I put them one on top of the other, and I put this weight at the bottom, Fg, it's the same weight as this one, right, or this one. It's just only one. So that means they're both experiencing that same force now. The tension is the same in both of these, and that means I'm getting delta x plus another delta x down here. By putting the springs like this in series, what's happening is I'm actually making one now weaker spring. So I'm going to get a smaller spring constant. But let's see how we can do that. Right? Right. Now we're going to assume that we don't know if these are the same springs or not. We just got two different springs. But here, right, it's going to be, imagine I've got one weight attached, right, a weight attached here, a weight attached here. I get some delta x, and then one of these weights I attach here again, and now I'm adding up these two delta x's, right? So my equation for this one is F equals K1 x1. Okay, and then here I've got F equals K2 x2. These might be different springs, so I'm getting different stretches. And then down here, I'm getting F equals K total times X total. And this X total is X1 plus X2, right? And I want to know, how does this compare to these? So F equals K total. X total is X1 plus X2. Right. Now, X1 is going to be F over K1. And X2 is going to be F over K2. So if I plug that in here now, look at what I've got. F over K1 plus F over K2, because that's X total, so I plug this in here. And I divide this. F over K total equals F over K1 plus F over K2. And all my F's cancel out. So 1 over K total is 1 over K1 plus 1 over K2. So the way we find the effective spring constant when I have springs connected in series is like this. Right? And we just derived that. This is another derivation that you'll have to know how to do. You may have to do this on the test. One thing to keep in mind, if you only have 2 springs, there's a shortcut. If you only have 2 springs, right, only 2, it's important, then K total is the product over the sum, K1, K2 over K1 plus K2, because that's what you would have to get. If you solved it that way with just 2, right, you could find the common denominator, add the fractions, and then flip, and that's what you would get. But, let's see. Now, if you're adding them just 2 springs in parallel with each other, now it becomes a little bit different. Okay. Okay, so we imagine that we've taken 2 springs, they might be different springs, and we've attached them in some way, right, maybe different points here along the way, so that they both have the same stretch. Right. And so if I draw a free body diagram of this thing, I've got the force of gravity, the force of the first spring, and the force of the second spring. Right, so this is then the total, let's call this F total. This is the total downward force. And so I write out my rule here, right? F total is equal to F1 plus F2. Okay, well that's good, that's the forces. Now let's write out the Hooke's law for each of these things. So F1 equals K1 times X. Now the thing that I've done here, because of the way I've attached these springs, I've got the same stretch on all 3. I just arranged it that way. And so I'm just going to leave this as X. F2 is K2 times X. And then F total is equal to K total times X. So I can take these and plug them in. So F total is K total times X. That's equal to, F1 is this, K1 times X plus K2 times X. Now I can just divide by X, and I get K total is K1 plus K2. So the effective spring constant when I'm attaching springs in parallel is just the sum of the 2 spring constants from before. Right, so this is another derivation that you might need to know how to do on the test. So the next slide is kind of a summary in general, right? The work is integral f dx. For Hookean springs, this is our summary. Example 1, we've got 2 springs, spring constants K1 and K2. They can be arranged either together, alone, in series, in parallel. And so what we're looking at is K2 is greater than K1. Which graph represents K1, K2, and these things? When you look at a graph, again, it's always important, what is the graph telling you, right? Introduce yourself to the graph, say, hello, graph. I see you are. And this one is F versus X. So then in that case, right, we know F equals Kx, so then K is F over X, and then that would be the slope of this graph. Rise over run, K is representing the slope. So the steeper it is, the bigger K is. And so what can be the steepest? How do I get the most K? By arranging them in series, right? Or in parallel. So in parallel, then D matches up with this. This has got to be D. And then they're always weakest when I have them together in series. And so that's got to be C. That's going to be this one down here, lowercase c. A little confusing. We've got letters on both of these. So let's just, you know what, let's just say this is in series. This is in parallel. And we know that K2 is greater than K1, so this has got to be K2 alone, and this has got to be K1 alone. Okay, so that's it. Let's take a look at example 2. We have an AP Physics student finds that he can stretch the same spring 1.3 times as far as an AP Bio student. It's a little, some fighting words. So we want to know what is the ratio of the forces they can apply, the force of the physics student compared to the force of the bio student, and then the ratio of the work done by each. Okay. Well, the force of the physics student, so the force of the bio student, well, F equals Kx, right? So it's K, the same K, and then it's X times 1.3. We'll say X is how far the bio student can pull this. So the ratio ends up just becoming 1.3. So the answer to 1A, to part A, is 1.3. But the work done, that's a little different now, right? Because the work done is the work of the physics student over the work of the bio student, an integral. Fx dx over Fx dx down here. And so this is from 0 to x. This is from 0 to x times 1.3. So this one's going to end up being, see, do we know? So we're just assuming this is kx. So this is 1/2 kx squared from 0 to x times 1.3 over 1/2 kx squared from 0 to just x, right? So these all cancel out, and this is then going to become 1.3x squared over x squared. So these things cancel, and I'm left with 1.3 squared, which is about 1.69. That's the ratio. He does 1.69 times as much work as the bio student. So good job, AP Physics student. Let's take a look at example 3. A 250-gram block drops 1 meter onto relaxed vertical spring. Okay, we've got something dropping. We've got a spring. This is going to be a conservation of energy problem, right? We want to start analyzing, like, what category does this problem fit into? Is it a Newton's laws problem? Is it a work problem? Is it going to be both, right? Momentum as we move on. The block becomes attached to the spring and compresses 4 centimeters before momentarily stopping. Right. So a bunch of things we're looking at here. A, what is the speed of the block just before it hit the spring? All right, so we imagine something like this. We're going to put the spring in a little bit of a well. Here's the block, and it drops 1 meter. That's the distance here. Okay, and then this is it at some later time, right? When it reaches compression, it compresses 4 centimeters before momentarily stopping. So this is it when it has compressed. And so this was 0.04 meters from here to here, right? Okay, so anyway, let's do A. We can do this a couple of ways. We can do this as a mgh, we could do this vf squared equals vi squared plus 2a delta x, whatever you want to do. If we say that mgh equals 1/2 mv squared, m's cancel out, so you get 2gh, the square root of that is going to be the v, and so you get 2 times g, so 10 times 1, it's about, what is that, 20? Square root of 20. So this is going to be 4.47 meters per second. Okay, and then B now we're going to do this in terms of gap C. B, we want to know the spring constant. Okay, so what do we have at first? We're going to take it from the point where it reaches this here, so kind of between these two. The point when it reaches this point, then it has kinetic energy and potential energy. So if I'm looking at gap C, then I've got K plus UE plus UG equals K plus UE plus UG. When it just hits the top of the spring, it doesn't have any elastic potential energy, but it does have kinetic and some gravitational potential energy because it's still above a little bit, right there. Later on, when it comes to rest here, these are out, and I only have elastic potential energy. So I have 1/2 mv squared plus mgh equals, and then this is just 1/2 kx squared. And I know all these things, so then I can substitute them in and find what k is. Notice also 1/2 mv squared here is equal to this from before, this mgh. So we could even put that in. Might make things even a little bit easier, right? But if we leave this, I can multiply everything by 2. I just want to simplify as much as I can. Plus 2 mgh is kx squared. So this is going to be mv squared plus 2 mgh over x squared equals k. I plug in my numbers here. M is 0.25. This is going to be 20 total, right? The square root of 20. 2, m again, 0.25. G is 10. H we can use as 0.04 because we're talking about this height now, right? As it's hitting the spring, so 0.04. And then x squared is also 0.04. And you square that, and it ends up coming out to about 3.3 times 10 to the third newtons per meter. Okay, now if the speed at impact were to double, what would be the maximum compression in the spring? So same spring, everything's the same, except what we're doing is we're going to double what V is. So if we double V, now we want to know what is the new X. So let's do C over here. Right. So for C we've got 1/2 mv squared plus mgh equals 1/2 kx squared. If I multiply everything by 2 and then divide by k and then take the square root, that'll be really nasty, but that's what we have to do. So I've got mv squared plus 2 mgh over k, and I take the square root, and that's equal to x. Right. I need to be careful here though because x is also h. Right. However much, if I'm kind of moving this around, then I'm also changing how high it is from the place where it ends. So I actually can't do that. So this is mgh, this is also mgx. Right. And I don't know what that is. So now, if I look at what I have here, this is going to be 0 equals kx squared minus 2 mgx minus mv squared. What I have is a quadratic equation. And since it's a quadratic equation, I plug in k, 2mg, and m. And what we're going to get, right, and for v I'm going to plug in 2 times the square root of 20, because square root of 20 was our velocity from before. And when you do all that, you should end up that x is equal to 0.079 or negative 0.077. And we're looking for the positive number, so it's going to be this. This is our new compression of the spring. Okay, and that's it for 7.7. Now we're going to look at section 7.9b, so we're continuing our study of power. And what is power? Last year you learned that power is work divided by time. It's the time rate of change of work. So really it's W for some change in time, right? What we're going to look at now, right, the change in energy, delta E over delta T. But now we have calculus and we have a different way of expressing this. So we look at this now as dW dt, right? It's the time derivative of work that's done. But we also have, since we know that work is force times displacement, so F dot dx dt, then we can see it, and this is a dot product, then dx dt is velocity. So this is F dot v, so that's Fv cosine of theta. And these are all vectors, or rather here we're just looking at the magnitudes. So we've got that. Don't forget this formula. You're going to want to know that on the test. It's a little one that's easy to forget. But force times velocity gives you power. So here's an example, right? You've got a 1,500 kilogram car accelerating uniformly from rest to 10 meters per second in 3 seconds. Find A, the net work done on the car. All right, so A, work is Fd cosine of theta. This is going to be 1 because it's accelerating. The force and the displacement, we assume, are parallel to each other. And then the average, so the net work done, we're still doing this. So this is 150 kilograms. What we're looking for here is delta x, or dV, right? And so this is V average times T. So what we're going to have here is, and then this is, F is MA. So M is 150 kilograms, rather 1,500 kilograms. The acceleration is 10 meters per second minus 0 meters per second, divided by the time, which is 3 seconds. And now I want V average times T. So average velocity is 5 meters per second. And the time, again, is 3 seconds. So these things cancel out. So I get 1,500 times 10 times 5. I think that comes out to 75,000 joules. All right, 5 times. Yeah. Okay. So then part B, now we want to know the average power. It's average power, so we're not doing this in terms of calculus. But P average is work divided by the change in time. So the work was 75,000 joules, and the time is 3 seconds. So that's going to come out to 25,000 watts of power. And next one, it says the instantaneous power at 2.1 seconds. So when we're looking at instantaneous power, either it's dW dt or F times V. So at 2.1 seconds, we want to know what the velocity is at that point. So we're going to do similar thing to what we did here. So this is going to be P times T. This is P of T. So M times A times. Now we want to know what that final velocity is. So we're going to use VI plus AT to figure out what the velocity is at that point. And then this is force times the velocity at that point. So M is 15,000 kilograms. The acceleration, same thing we figured out before. 10 over 3. That's just like that. And then the initial velocity is 0. But we're looking at the acceleration here, 10 over 3 times 2.1 seconds. Okay. And I think this comes out to 35,000 watts. All right, so that's an algebraic example. In example 2, now we're going to look at this a little bit in terms of calculus. So, stone of mass m is dropped from rest through a distance d under the influence of gravity. Find general expression for the net force. This one should be easy. All right. F net is mg. We don't talk about air resistance here, so it's just force under gravity. So the net work done on the stone, expression for the net work done is going to be Fd cosine of theta. This is 1. The force is mg, and the distance is given by 1/2 at squared, right? D equals VIT plus 1/2 at squared, but this is 0, so this is my expression for the distance, so 1/2 at squared, but A is g, so this is 1/2 mg squared t squared. Looks kind of funny, right? We don't see expressions like that. This is the kind of thing you need to get used to doing, that they're going to put on the AP exam, and they're going to expect it to be something like that. Just an expression that you haven't seen before, but is still true for the given situation. So now C, I want to know the instantaneous power. Realize this is an expression for the work. If this is the expression for the work, then the power as a function of time, I can just take dw dt. And so I take the time derivative of this, and I end up with mg squared t. That's it. So that's the answer to part C. So now we're completing the tables for parts D and E. And it's going to look something like this. 1, work, power. When you plug the numbers in, that's how it goes. And then the graphs, what do they look like? Here's the quadratic. This graph is going to look something like this. All right, so this kind of looks like a quadratic. And then power and that one looks linear because the derivative of a quadratic is linear, which is what we expect because we saw what the functions look like. And work was a quadratic function, and power was a linear function with respect to time. All right, example 3, another one. All right, so we've got a constant horizontal force, and we have a constant speed of 5 meters per second. So we want to know the work done by the applied force in 1 minute. Now we want to be careful that we're distinguishing here between what's doing the work and what's not. Ultimately, it's moving at a constant velocity. So the net work done on this object is 0. No work, it's not changing its amount of kinetic energy, it's not going up or down or anything like that. That means that this force is doing work on it, but friction is also doing work on it in the opposite direction. So let's take a look. The work done by the force in 1 minute. So the work is FD cosine theta. This is 0. So the horizontal force, right, that's how we know this is 0 because the force and the displacement are horizontal and therefore parallel. So cosine of theta is, sorry, not 0, but 1. If it was 0, that wouldn't work. So this is 10 newtons, and it's moving at 5 meters per second for a time of 60 seconds. So this ends up being 3,000 joules. That's how much work is done by the force. Now we want to know the average power. So power is work divided by time. Work was 3,000 joules over 60 seconds. Notice I'm just dividing by the 60 seconds again. So it should be 5 times 10, and I get, 50 watts. That's part B. Part C, the work done by friction. So notice that we've got no change in the overall kinetic energy. That means that the work done by friction has to be the same as this. However, the friction is taking energy out of the system, and so it's negative 3,000 joules. But we can show this mathematically as well. The work done by friction is FD cosine theta. Now what direction is theta? If we draw the free body diagram here, here's the applied force, but here's the friction force, and this is the displacement. So the friction force and the displacement are 180 degrees. So this is negative 1. So I do the same thing here. 10 times 5 times 60 times negative 1, and I get negative 3,000 joules. So we want to know what's the net work done? 0. OJ, 0 joules of work done. The change in kinetic energy, 0 joules. No change. And the rate at which energy is dissipated to the ground as heat. Okay, so now the rate of energy dissipation, a rate of energy change is power. And so what we're looking at here, that should be an E, F, is the change in energy divided by time. So that's P average. So that's work divided by time. So this is negative 3,000 joules, because what's contributing to this energy, the heat energy, it's the friction. And so it's negative 3,000 joules divided by 60 seconds. And I get negative 50 watts. Right? That's the rate at which heat is being produced and energy is lost due to friction. Right. One more example. This is a review example. So we have a 2 kilogram block. It's forced against a horizontal spring of negligible mass, compressing the spring to 0.15 meters. So I'm just going to draw this. Here it is when it's compressed. And we'll say this is 0, and this is 0.15 meters here. Or we can say negative. It's being pulled back. When the block is released from rest, it moves 60 centimeters across a rough horizontal table before coming to rest. The spring constant is 2 newtons per centimeter. Find the initial applied force. So A, initial applied force, FA. So this is the force applied this way, is Kx. So it's 2 newtons per centimeter times 15 centimeters. This is 15 centimeters. As long as I keep everything in centimeters, then I can do this. I can use newtons per centimeter. And this works out then to 30 newtons. All right, B, the applied work that's done, right, this is f dx, integral f dx, from 0 to 0.15. Now I'm going to put everything in terms of meters. And so this is 0 to 0.15. F is kx. dx, just to show you the calculus again, but this is going to work out like it normally does. So 1/2 kx squared from 0 to 0.15 meters. And so this is going to be 200 newtons per meter. I converted from meters to centimeters there. Divided by 2, so 1/2 k. And then the x squared. Oh yeah, the location here is negative 0.15. I'm going from 0 to negative 0.15. So negative 0.15 meters squared minus 0 squared. And so I end up with 2.25 joules. That's the amount of work done in compressing the spring by the applied force. All right, how much work was done by the spring? Negative 2.25 joules. So now I want to know the change in kinetic energy from the time the block is released until it comes to rest. And so the answer there is going to be 2.25 joules. When it's released, actually, from the time it's released here to the time it comes to rest over there, what's the velocity? You know, the initial velocity is 0 from the time it's released, and then when it comes to rest, Vf is 0. So delta Ke, the change in kinetic energy, is 0 joules. Now we want to find what mu K is, what the coefficient of friction. Let's see, it comes to 60 centimeters across a rough horizontal table. So it goes 60 centimeters. And we know that this block is 2 kilograms. Okay, so I know it has this much energy, 2.25 joules, to start with. That means that by the time it comes to a stop, it has used up 2.25 joules of energy. And so the elastic potential energy it has here, UE, is equal to the work that's done by friction. So this is 2.25 joules. All right, I'll write that clearer. And then the work done by friction is going to be the force due to friction times the distance. Right. The force due to friction is mu mg, and then times the distance. The distance is 0.6. I'm solving for mu, so mu is going to be equal to 2.25 joules, that's this, divided by mgd. So 2.25 divided by the mass, which is 2, g, which we're going to just use 10, and then 0.6 meters. And whatever that works out to, I don't have the final number. But we could probably do this. What's 2.25? That would be 9/4 times, and 0.6 is 3/5. So 3/5, and then I've got a 10 on the bottom here. So let's see how this cancels out. I get a 3 here, I get a 2 here, so 3 on the top, and an 8 on the bottom. 3/8. So that's going to be 0.375 or something like that. And mu K, because it's the coefficient of kinetic friction. I think that's right. I was just trying to do it in my head. And that's it for this packet. So welcome to Chapter 8. This is going to be about conservation of energy, potential energy curves, that sort of thing. First thing to talk about is some vocabulary. First of all, the datum. We're talking about something having gravitational potential energy. We have to set the height, but we have to set the height from a particular point. And we decide what that is. The datum is sort of the 0 point. If we're above that, then we have positive gravitational potential energy. If we're below that, then we have negative gravitational potential energy. All right. So that's what the datum is. Potential energy comes from objects that are in the system that are going to exert conservative forces. So in this system right now, if I'm going to talk about potential energy, then the objects in the system are the ball and the Earth. If we don't include the Earth in the system, then the force from the Earth is an outside force. And we don't talk about it in terms of potential energy. We talk about it in terms of work done by an external force. So we want to be careful about making sure we understand what's in the system and what's not. Same thing for springs, right? A spring is another source of potential energy. And so if we've got the spring in the system, then we talk about potential energy. If not, we're talking about the work done by the spring as an outside force. All right, so figuring out what's in the system and what's not is important. Conservative forces, this allows conversion from kinetic to potential energy. So Earth is a conservative force, or we could have something from outside, something pushing, and actually if it's outside, then we don't have potential energy. So again, conservative forces are just in the system. Earth is exerting a force, it's in the system, so it converts from potential to kinetic energy. Right, same thing with springs for now. We'll talk about other forms of potential energy, conservative forces in the system. Non-conservative forces are forces like friction in the system. So if this is rolling down a hill and there's friction or a block is sliding, then that would be a dissipative force, something that takes mechanical energy out and it turns into heat in the surfaces of the objects. And then there are also applied forces from the outside. So something like you could have a fan pushing, like a wind tunnel, somebody comes along and pushes something, magnets, whatever it might be, some outside force. And so what we get now is this equation. You guys learned, I think you learned bar charts last year. It's a way of looking at the total energy at the beginning, the work done, and then the total energy at the end. And all we care about are those, the final and initial conditions, and then whatever work is done in the middle. And we're going to see examples of this. This really, the rubber hits the road when we see the examples and you start working through this. But Ki is initial kinetic energy, Ui is initial potential energy, and that can be either gravitational or elastic potential energy. And then we look at the work done by applied forces. So if we've got a wind tunnel, something like that, adding energy, or taking away. If it's taking away, then that's just negative. That W becomes negative. The work done by non-conservative forces, that's the work done by friction, something like that, usually negative, taking energy, mechanical energy out of the system. And then we look at the end, kinetic energy and potential energy again. So here's the problem-solving strategy. Look at the problem and figure out all the forces involved. Do we have Earth? Usually yes. Do we have springs involved? Are there places where there's a wind tunnel, where there's friction, something like that? Split the problem into natural breaks. So look at the beginning, look at the end, and then look at all the things in between. So pick the section where there's the wind tunnel and figure out what that force and the distance is. Where there's friction, figure out what that force and the distance is. And then we put it all together in the equation. And then you're typically solving for something. So again, if we're looking at conservation of mechanical energy, like for example this example with the hill and the roller coaster, the total energy is equal to the total energy at A is equal to the total energy at B equal to the total energy at C. That's the whole idea, that energy is conserved. And if there are no non-conservative forces, if there are no forces from the outside, the total amount of energy just remains the same. Okay, so let's take a look at an example. We have example 1, a simple harmonic oscillator is set into motion on a frictionless surface with an initial velocity of 5 meters per second at its equilibrium. The mass of the oscillator is 2 kilograms. So it's set initially 5 meters per second. At this point, that means it's going to be going this way. It'll slow down and then come back. So it's going to be oscillating like this. And question A asks, what is the kinetic energy at maximum compression? When it's at maximum compression, this is all the way over here. That's where it's actually stopping. So at that point, the kinetic energy is actually 0 joules. All right. B, where is the kinetic energy equal to the potential energy? Okay. So what do I know about this? Well, I don't know what the total Well, okay. I need to figure out what the total amount of energy is. Right? How do I know that? Well, the total amount of energy is equal to, here at this point, what is the energy that I have? I've got kinetic energy, but I don't have any elastic potential energy because it's at the equilibrium. It's not compressed or stretched at all. So at this point, the kinetic energy here, that's the total energy. So the total energy is equal to the K at 0. And then what I want to know is where then is the kinetic energy equal to the elastic potential energy. But since K and U are equal to each other at whatever point this is, I'm just going to set K and U equal to each other. Since K equals U, then I can substitute one of these in here. What I'm looking for is position. Right? If I substitute K, then I'm going to find the velocity at that place where these are equal. But instead, I'm going to put U in here. So I'm going to say that K naught, so K at 0, is equal to 2 times UE. All I did was I substituted, since these two things are equal, I substituted this in here. So I've got UE plus UE, and I get that. So K0 equals 2 UE. And what this looks like then, let me go up here, a little more space. So this is 1/2 mv squared plus, or not plus, equals 2 times, and then the elastic potential energy is 1/2 kx squared. I know m, I know v, right, at position 0, and I know what k is, so now I just have to solve for x. So this cancels out with that. I'm going to divide k over to this side, so I'm going to have m v naught squared over 2k equals x squared. So x, this position, is m v naught squared over 2k, and I take the square root. Simplify a little bit more, v naught root m over 2k. So this is 5 meters per second. The mass is 2 kilograms, and 2 times, and this is 20,000, and I don't have the actual number, so I don't know what that is. But whatever you get here, you'll end up with plus or minus some position. Again, this is the important part anyway, setting it up. Right? And so what we're saying is, at that point, that's the place where the kinetic energy and the elastic potential energy are the same. Right? And then part C, what is the maximum displacement of the oscillator? Let's go back now and look at gap C and see how this works. All right. Let's look at the whole equation. Okay, I'm comparing two places. This is where I have my information, so I can use this as my initial point, versus the place where it has maximum displacement, whatever this is. This, let's just call it x. All right, maximum, does it say compression? Just says maximum displacement, so that's here or over there. This is my final condition. So in the initial condition, when it's here, I have kinetic energy. There's no elastic potential energy. Is there any work done by any outside forces? What's the system here? The system is the block and the spring. That's it. No work is done by any outside forces, so this is 0. It says we're on a frictionless surface, so there's no work done by non-conservative forces. At this point, this is the place where it's stopping briefly, like we saw in part A. So part A is helping lead to this. That's where the kinetic energy is 0, so that's 0. So now I take what I have from this equation and I put it in. So kinetic energy, 1/2 mv squared equals 1/2 kx squared. Right. Similar to what we had before, but how is it different? Well, I don't have a 2 in here. I'm not adding this up twice. Instead, what we're saying is all of this energy now is in the form of elastic potential energy. And now I'm just going to solve for x. So it works same way, and here what we actually end up with is 5 times 10 to the negative 2 meters. When you do the algebra and you solve for x, you should get that, which is really 5 centimeters. You can give your answer either way. Let's take a quick look at the graph. What would the graph look like for this? Let's graph the total energy, the elastic potential energy, and the kinetic energy. A is amplitude, by the way. So if this thing is oscillating back and forth here, what's happening to the, let's look at the this energy, the elastic potential energy. Well, at 0, the elastic potential energy is 0. And at the amplitude, that's where all of the energy is in the form of elastic potential energy. And at maximum compression, that, again, when it's at that negative amplitude, that's where all of the energy is in the form of elastic potential energy. So this looks like this. So elastic potential energy versus displacement looks like this. What about then the kinetic energy? Let's use a different color. Kinetic energy is 0 at the maximum amplitudes, but it's at its highest point at 0. So that then looks like this. So the orange here is kinetic energy. The blue is elastic potential energy. And this dotted black line is the total energy. So what we're looking at here now is we've got a box, spring, it's a frictionless surface, so the box is here where there's no stretch in the spring. So it's at its natural length, and then we let it go. So the box comes down and then stops at some point. So we want to know how far along the incline did the box slide. So we've got this distance here, x, however far the box slides. The force on this, so we want to know, at first it's got a certain amount of gravitational potential energy, and then there's work done on this. So the amount of gravitational potential energy is mg. Now we've got to be careful. It's not x, right? Because instead what it is, it's going to be this distance right here, this vertical distance that it's going to fall down. But we want to do this in terms of x because x is how much the spring stretches. Right? So mg, and this is going to be x sine of theta, this distance right here. Right? If we do a little bit of trigonometry, if this is the distance x, this is 40 degrees, and so this distance is x sine 40. Right? So that's the amount of gravitational potential energy it goes through. So what am I doing? I'm setting my datum here at that bottom point. Datum. The starting position is up here somewhere. Okay, and I can move the datum wherever I want, so I can do that. This is the amount of gravitational potential energy that's used up in it falling from here to here. That then converts to elastic potential energy. At the end, what I have is, now this spring is stretched. When I first release it, it's not moving, so kinetic energy is 0. When it gets down to the bottom, it reaches a point where there's no movement, so there's no kinetic energy there. There are no outside forces, there's no work done by friction. So all I have is gravitational potential energy at the beginning and elastic potential energy at the end, so this is 1/2 kx squared. All right, I'll cancel out an x, make it a little bit easier. What do we want to know? How far down the incline did the box slide? So we're looking for x here. So this is going to be 2 mg sine theta over k. That's what x is equal to. And so we get 2, the mass is 2, g, we're just going to use 10 sine of 40, and K is 200 Newton meters. That should come out to about 12.9 centimeters. That's how far it goes. The second question now is, what is the acceleration of the box at that instant? All right. So we're just going back to Newton's second law here. F net force equals ma. What are all the forces on the box at this point? All right. Well, one is the force due to gravity, and it's pulling down that way. And we'll say that we want to make that negative or positive. We'll make this negative. Plus the force from the spring, that's going to equal ma. So the force due to gravity is mg sine theta. So negative mg sine theta. Plus the force due to the spring, which is going to be kx, equals ma. Right. So when you plug these numbers in, x is the stretch in the spring, so we get negative 2 times 10 times sine of 40 plus k, which is 200, times x, which is 0.129, divided by, again, 2, which is the mass. That should give you an acceleration of about 6.4 meters per second squared. Right? And that, since I made this is the negative direction down, this force is positive pulling up, so my acceleration is in the same direction as that force up. Because what's happening? This box is coming to a stop and then changing direction and going back up that way. Example 3. Find the distance traveled by the block before it comes to rest. So at the beginning, this has some kinetic energy. It has gravitational potential energy. And then, is any work done by an outside force? No, because it's box and earth. Those are in the system. I've got gravitational potential energy. Is there any work done by a non-conservative force? Yes. Right now it's going to hit the friction there. And so the work done by friction is going to be negative because it's going to be taking mechanical energy out of the system. So this is going to be mg times mu. So this is the force of friction times the distance, which is given to me as d. And then at the end, I have zero energy. No kinetic energy, it's come to a stop. Zero potential energy because it's at our datum level. And that's it. So now all I'm doing is I'm solving for d. Right? I want to know what is d in this case. So I've got negative mu mgd equals negative 1/2 mv squared plus mgh, or rather minus mgh. So then I'm solving for d, so this is going to be 1/2 mv squared plus mgh over mg. That's it. Just leave it like that. We don't even have to plug in any numbers. Okay. And we can cancel out m, simplify this a little bit so it looks a little neater. 1/2 v squared plus gh over mu g. Interesting to notice then that the distance this goes is independent of the mass. Okay, example 4. So here we're finding the distance traveled by the block in the area where there is friction before it momentarily comes to rest. All right, so there's this. Oftentimes in a test or some type of problem set, there'll be something like this to indicate that there's friction along here. So this block is coming this way. That's a force. So we draw the arrow over here. So this is V1 going that way. And there's no friction here, but once it hits here, there's going to be some friction. And it's saying that it's going to momentarily come to rest. So initially it has kinetic energy, so 1/2 mv1 squared. Nothing else at this point. That's all the energy it has. It doesn't have any elastic energy. It doesn't have any gravitational potential energy. But then once it hits here, what this is saying is that there's going to be some friction exerting a non-conservative force. So this is going to be negative mu mg, and I'll just call this x. I'm calling this x because however far this goes, that's also the compression of the spring. That's the key to this problem, recognizing that this, how far this goes, is the same as the compression of the spring. So that's going to be 1/2 kx squared. All right. And then however far it compresses, that's the place where it comes to rest, so there's no kinetic energy at that point. So all I have on this side is elastic potential energy. And I don't have any numbers, so all I'm doing is I'm solving for x. That's all I'm looking for? Yeah, just the distance traveled. So, since I'm solving for x, I have x squared and I have x. This is going to be a quadratic equation, right? Sorry. So I've got negative 1/2 kx squared minus mu mgx plus 1/2 mv1 squared equals 0. And now I apply the quadratic equation. And so this comes out to x equals negative mu mg plus and minus square root of mu mg squared plus 4 negative 1/2 k. This should be minus, but then it'll be plus with that. Times 1/2 mv squared. That's positive though, so I leave that. All over 2a. So this is going to be 2 times 1/2 k. And we can simplify this a little bit, right? Multiply the 4 into here. So the 4 and the halves go away. This becomes positive. This just becomes k. Once you simplify it, then that's your answer. The other video is getting too long, so now this is part 2. These last 3 examples, 6, 7, and then problem 65 from the textbook. So example 6, the way this works is that we're going to use GAPC up until this point. This is all conservation of energy, right? So this, I have gravitational potential energy, I have elastic potential energy to start with. I don't have any kinetic energy, right? It's being released from rest. It's just released, which means you're just letting it go. And then I've got this non-conservative force. So the energy, I'm figuring out what the velocity is here at this point. So I'm setting my datum here. Right. So at this point, all it has is kinetic energy. So I can solve for the velocity here, and from that use projectile motion kinematics to figure out how far this goes that way. All right. So let's take a look at our GAPC equation. This is compressed, so I've got 1/2 kx squared plus mgh1. That's it. That's all the energy I have at the beginning. And then the work done by a non-conservative force is mu mgl. So L, L1, just L, equals 1/2 mv squared. And v is the velocity at that point. That's it. I don't have this in terms of any numbers, so all I'm going to do here is solve for v here. So v is going to be, let's see, can I simplify anything else? I can multiply by 2. That's about it. So this equals, do I divide by m? Well, if I divide by m, then this goes away, and I just get this over m. So v is going to be the square root of this. So the square root of kx squared over m plus 2 mgh1 minus 2 mu gl. That's the horizontal velocity at this point. Now I want to find out how long is it going to take for this to reach the bottom here. So y equals 1/2 gt squared, but y here is actually h2. So this is H2. So T is the square root of 2H2 over G. That's the time it's going to take to fall. The distance it goes then is going to be this speed times this time, because this is the horizontal speed. That horizontal speed times the time it takes to get down is going to give me the distance that it goes. And so this is then going to look like, so I'm multiplying this into here. So the distance, do we have some S? It's going to be the square root of, so then 2 times this is going to be 2h2 kx squared over mg plus, now this is going to be 4, oh, sorry, this m shouldn't be in here, getting rid of that. 4 g's cancel out, so I just have h1 times h2, and then minus 2 times 2, so it's 4. Mu, g's cancel out, LH2. Let me check. How does that look? Yep, it's nasty, but just leave your answer like that. That's the answer. Okay. Let's take a look at example 7. I'm just going to talk through this one. The idea here, the block travels with initial velocity, so we've got numbers. So it has an initial velocity, but we need to pay attention to the heights here because we ask ourselves at the beginning, what type of energy does it have? So initially it's got kinetic energy. All right. Does it have any potential energy? Well, if we look at the heights, we see that the first hill is 4 meters up, but the last hill is 6 meters down. So I'm going to use that bottom height as my datum. That means we're starting off at a height of 2 meters. So plus mgh. Okay. Now I'm going to look at the work done by all these other forces involved. So first of all, I have friction going up the hill. So what is that friction going to look like? The hill's like this. The block is going up. What is the force of friction on this? The force of friction is going to be mg mu mg cosine theta. Right. Mg cosine theta is the normal force. This is, and this is what mu is. So then the work done by this force is mu mg cosine theta times just that distance d. So I'm going to call that d1. So minus mu mg cosine theta times d1. Okay. Then I have a 12 Newton force being exerted on it in a wind tunnel. So that's a positive force. It's being, right, it shows you the distance or the direction that's going. So plus, let me just call that FA. It's an applied force times D2. And then, what else do I have? Then some more friction. So this one is just mu mg. So this will be minus mu mg d3. And then going down that other incline, I already took into account the potential energy, right? All we care about for the gravitational potential energy is the beginning and ending points. So this last one is going to be minus mu mg cosine theta d4. That's it. Equals 1/2 kx squared. At the end, it hits this spring, and it'll be compressed some distance. That's all we're asking for. So we're taking our ending point when it's at maximum compression. All right. So that's really it. All the physics is done. At this point, the only thing that needs to be done is you plug in all of the numbers and you solve for x. I'm not going to go through that and waste time on the video, but if you go through, you should end up with x equals 5.3 meters. Okay, and so even something like this, where there are all these different things, you've got, kinetic energy, you've got gravitational potential energy, you've got 3 different places where there's friction, there's a wind tunnel, and then a spring at the end. All of that can just be put into one big equation. right? Your initial energy conditions, all the things that are adding to or taking away from the energy in the system, and then whatever the final total energy is at the end, and you solve. Okay, that's it. All right, this last example from page 195 in the textbook. This one can get a little bit tricky. So let's take a look at what we're doing here. We've got the elevator falling down, and it's going to hit some spring. This is 1,800 kilograms. Let's just write down the things that we know. This distance, so it's 3.7 meters above the spring, above the top of the spring. That's important to know. And the spring has a constant, K, of 0.15 meganewtons per meter. And then the safety device clamps on the cab so that there's a constant force of 4.4 kilonewtons opposing the cab's motion. So the idea is that, right, those clamps click onto these poles. So what I now have is a friction force of 4.4 kilonewtons, whether it's moving down or up, because we're going to have some bouncing going on. And so the first thing we want to know, find the speed of the cab just before it hits the spring. So it's falling some distance, this distance 3.7 meters. Right. So initially, I'm going to set, just for part A, I'm going to set this as my datum. Right, and I can change this as I go to the different parts. I just have to stay consistent. So I'm going to set this as my datum. I have mgh. I've got gravitational potential energy. Now I don't want to go right to the end yet because there's some work being done by friction. So mgh minus this force of friction, but the force is given over some distance, right? What's the distance it goes? Well, it goes the same distance, h. So minus the force of friction times the height equals, now I've got 1/2 mv squared. So I plug in my numbers. So v is going to be the square root of 2gh minus the force of friction times the height over m. This is also going to be 2. So this is equal to 7.48 meters per second. Great. Part B. Find the maximum compression of the spring. Keep in mind that the friction force is still acting on this thing. So what does that mean? So let's set this up now. I'm going to draw another diagram. Here it is. It's on the spring. But now I'm going to set my datum here at whatever the compression is, x. This is the initial moment, and then it's going to compress the spring some distance, x. I'm setting this as my datum so that I can have the distance it goes along the rails, I can have the distance it goes down, so the gravitational potential energy, and the compression of the spring, all the same thing, all the same variable x. So for B, I'm going to use this now. I'm talking about this thing. It has gravitational potential energy, mgx. It also has kinetic energy, 1/2 mv squared, and this is this velocity. We are losing energy due to friction, so this is going to be minus the force of friction times x, because that's the distance it goes. The same distance it falls is the same distance it goes, and that's the same amount of compression there is in the spring. At the end, it's reaching our datum that we set. It's coming to a stop, so there's no kinetic energy. And so now I need to solve for x. And so as nasty as this is, we're going to end up having to do another quadratic equation. So this is going to be negative 1/2 kx x squared. And I've got this and this, so I'm going to have plus mg minus the force of friction times x plus 1/2 mv squared, all equal to 0. Questions about that? Write them down. And so now when we plug in our numbers here, again, I don't want to go through it now to waste time in the video, but we plug in the numbers and use the quadratic equation, we should get that x equals 0.915 meters. Okay. So now C, find the distance the cab will bounce back up the shaft. So this fell, and it's going to bounce back up. Well, why won't it go to the original height? Right? It's not going to go to the original height because we've got this friction force. So this friction force is taking energy out, but so that's why it won't go back to the original height. We have to do a new calculation. But we do have to take into account the friction force even on the way up. It's still, this friction force is still acting on it as it goes up. So let me do a new drawing here so we can figure out what's going on here. I already know the compression of the spring, so that's good. So this is it compressed. I'm going to use this as my datum, 0, because whatever height it then gets to at some later time, so this distance here is h. This is where it is at some later time. I'm going to measure the distance from there. So what does our equation look like here? At this point, it has no kinetic energy. It has no gravitational potential energy because it's at 0. All it has is elastic potential energy, and it's the same as what it had over here. So this is 1/2 kx squared. Now we're going to be losing energy due to the friction, and the friction is going to be exerted on this thing the whole height. As the spring is extending and as it's going up into the air above the spring, but that's that whole distance h equals mgh at the end. That's all we got to do. So then we plug in our numbers. X we already know from here. Right? Or you could use this if you happen to have solved for this, but you didn't because we did this. But you could plug that in. But I'm solving for h. So you know the algebra. And the answer that we get is 2.8 meters. Let's take a look then. It says, find the approximate total distance the cab will move before coming to rest. Okay. This one we need to be careful the way that we set it up. So here's the cab at some earlier time, or no, rather at the initial moment. Right? It's this some distance above here, and we said we already know that that's 3.7 meters, right? And then at the end, it's going to be compressed some distance x. So this is x in here, and this is whatever that initial height was. I want to set this as my datum so that my final condition is just 1/2 kx squared. I don't want to have any other energies there, like potential energy, kinetic energy. And kinetic energy won't be there anyway because it's going to come to rest. That means that this height that I actually have to put in above my datum point is h plus x. So I've got mg h plus x. This is the potential energy it has at the beginning. Notice we're setting this up different from in part A. Why? Because I've set a different datum. I'm not going to the datum I had before. It's not coming to a rest and then springing it back upwards. This is just coming to rest on here. And so it's a different amount of compression from in part B. And I don't know what that is. So I've got this, and then I want to know the total distance that it goes. So minus the force of friction times d, that total distance, whatever it is. Okay. So I know this height. That was 3.7 meters. But what about X? How do I figure this out? How do I figure out how much compression there is? Well, it's just resting on there. That means if I make a free body diagram of this, I've got the force of the spring that way and the force of gravity this way. The force of the spring is equal to the force of gravity. That means that mg is equal to kx. So I can use this, mg over k, to find what x is. And then I plug this in here and here. I know the friction force. This is the work done, right? The reason I'm putting this in here, by the way, this is the work done that entire time. The total distance, it goes down and up and down and up again. This force of friction is being exerted on it the entire time. And the whole time, it's negative because it's always taking energy out of the system. Right? Realize this negative is not a direction, it's not a vector, it's saying that we're losing energy. It's a subtraction from the total amount of energy. So I know H, I know X now from this. I can plug that in, mg, k, f, all that stuff. Plug the numbers in, do the algebra, the arithmetic, and you should end up with 15.4 meters. Okay. And that is how you use GAPC. All right. Welcome to the last section in Chapter 8 and in this unit. Today we're going to talk about the potential energy graphs and how they're related to force and change in energy and the stuff like this. We're going to start with stuff that you already know and then get to something that we haven't learned yet. Imagine that we've got some object, some ball, and it's going to be falling. As it's falling, it's losing gravitational potential energy, but it's gaining kinetic energy, right? And so the change in the kinetic energy is equal to the change in the potential energy. Right? So if this, but this is gaining and this is losing, so this is going to be a negative. Right? Another way to think of it is that if we're not talking about potential energy, but thinking of gravity as an external force, that force is doing work on this object. So the change in the work done by gravity is equal to the change in the kinetic energy. But the work done by gravity is equal to the negative change in potential energy. Right? So work done by gravity is equal to the negative change in potential energy. Right? As gravity does more work, think of it that way, then it loses potential energy. Right? It's losing the potential energy that it has because of that force, because of the gravitational force. Okay, and so how do we calculate work? Well, work is integral f dot dx, right? And that's equal to negative of the total change in potential energy. So we end up with then the negative, the change in potential energy is the negative integral of that force dot product with dx. It's like we're adding up all the little works that are done over time as this thing goes down. Here it's a constant force, so we don't need the calculus, but we will need the calculus later. This is going to come in again and again and again. Don't forget your units. Your units here are important for thinking about what this relationship is. What is potential energy? Potential energy is in terms of joules. What is a joule? It's a Newton times a meter. So if I want potential energy, how do I get that from these units? I'm multiplying. And what is like multiplying? Integration. Right, and then we can go the other way. If we rearrange this, I see, oh look, this is a dx. If I divide this over to this side, right, watch what happens. That the force is equal to negative du dx. If I have some function that expresses the potential energy as a function of position, not as a function of time, but as a function of position, I can take the negative derivative of that, and that gives me the force on that object as a function of position. Okay, so what does that mean? We've got this graph in the fourth slide of this presentation, and it looks something like this. It's the top graph is potential energy, and it looks kind of like this, right? And then this is the force graph, right? Remember, force is the negative derivative. So the derivative of this is 0. And here the derivative is negative. And it's increasing. It's reaching some high point around here. This is negative, so this is going to be positive, right? So I'm going to put the high point around here. and then it's going to 0. So at this point, right, the derivative here is 0. So this is going to be coming down like that. And then reaching, this is a large positive slope. So I'm going to make it a large negative, right, a negative value. That's the low point there. And then again, 0 at this point. So this is 0 slope. If this is negative, the derivative of this, right? This is potential energy, this is force. And so now again, it's at the steepest here. So at this steepest point, that's where it's going to be at some high point. And then again, 0. And then some steep, this is steep and positive, so this is going to be down negative. And at this point, it'll be back to 0. Right? So then the force graph looks something like that. Okay? And this should reach that point. Okay. Again, it might be a little bit confusing thinking about the negative derivative, but it works. It works in terms of the math and the calculus, and we're going to be using this again and again. Right now, we're actually starting pretty simple. So then we've got another example, right, using calculus relationships now. So we're given a function. Here's the function of the potential energy as a function of position. So it's 2x plus 3x squared. And so we want to know the force applied. What is the F, the force at 3 meters? All right. So first of all, let's take a look at, let's do what we know how to do. Take the derivative, and we'll make it negative, and then we'll plug the numbers in, right? So negative du dx is what the force is. And so the negative derivative of this is going to be negative 2 minus 6x. Right? So then F at 3 is going to be negative 2 minus 6 times 3, which is 18. So we're going to end up with what? Negative 20 newtons. Okay. And we've got these graphs here so we can see what do the graphs look like, how are these related to each other. And we have these functions, this and this. Here, if we factor out x, then we get 2 plus 3x. And so our zeros for this are negative 2/3 and 0. So for the potential energy graph, I've got 0 and negative 2/3. And so this is going to look like this. And then for the force graph, here I've got a y-intercept of negative 2 and a slope of negative 6. So 1, 2, that's like that. And then this is going to be reaching 0 around 1/3 or so. Negative 1/3, this negative 2, and it's linear. So it looks like that. This is the negative derivative of that function. Okay. So next one, using calculation relationships, B. Now we're given the function as force. So Fr is 2r plus 3r squared. It's the same as before, except now we've got, now it's force and not potential energy. And so now we want to know what is the change in potential energy. So delta U from 1 to 3 meters. Okay, so the change in potential energy is the negative integral of F dot, in this case, dr. And so we're going to take the negative integral of 2r plus 3r squared dr. Let me come back over here. So this is going to be negative r squared minus r cubed. That's it. And now we're going to be going now, this is a definite integral from 1 to 3. So I plug in my numbers here. And do we have any shortcuts? Nope. So negative 3 squared minus 3 to the third power. And then minus, so plus 1 plus 1. So this is negative 9 minus 27 plus 2, so negative 36, so negative 34 joules. Right. And then what do these graphs look like? Well, again, this one is like the graph that we had before. Right, it's going to be like this. Force, this is going to be 0 and negative 2/3. And then this graph, if we take a look at it, it's third order and it's negative, so it's going to be going down like that. Okay. Okay. So what we can do is we can find that the force that a particle feels at a given position on a potential energy curve, right? Again, F is the negative slope of the tangent line. And by looking at potential energy graphs, we can also figure out how much kinetic energy there is if we're told how much total energy there is in the system. All right, so take a look at example 1, where it's got that big graph thing next to it. Right, so it's a 2 kilogram body in one-dimensional motion. So it's moving along a single path, so up and down or left and right, due to a conservative force that does work on it. So there's some force, it's conservative, so it's part of the system, and it's adding to or taking away from the potential energy in the system, and so contributing to the kinetic energy as well. The total mechanical energy is limited to 7 joules. Now if I look at where 7 joules is, that's above. So at time 0, or rather position 0, I have 6 joules of potential energy, but if there's a total of 7, that means I've got 1 joule of kinetic energy at position 0. You see how it's just the difference between whatever the value is on the potential energy graph and how much total energy there is. Okay. So for this example, in 1, it says find the kinetic energy of the body at 4 meters. If you look at 4 meters, it's at it has 0 joules of gravitational potential energy, and so since E total is 7, it's going to have 7 joules of potential energy. For 2, it says find the kinetic energy of the body at 7 meters. So you look at 7 meters, it's at 3. The total, so at 3, at 7 meters, you can see it's got 3 joules of potential energy. That means it's got to have 4 joules of kinetic energy. All right, and then at 9 meters, you look at where 9 is, it's got 1 joule of potential energy. That means it's got to have 6 joules. 6 joules of kinetic energy. And then at 12 meters, it's got 4 joules of potential energy, which means it's got 3 joules of kinetic energy. And it says find the speed of the body at 12 meters. Well, so it's got 3 joules of kinetic energy. So K is 1/2 mv squared. It's a 2 kilogram object. This is 3. So 3 joules is equal to 1/2. It's a 2 kilogram object. V squared. Those cancel out. So it's a square root of 3 meters per second is the velocity. All right. Now the next one, this is different because now we're limited to having only 5 joules. If you read it, total mechanical energy is limited to 5 joules. What it means then is that this object, whatever it is, can't get past about 2 meters. It'll never go to the position 0. You can think of this just like a roller coaster, right? However much energy it has at the beginning, and then it's transferring from kinetic to potential. But here, if it's limited to having only 5 joules of energy, total energy, that means it can't have 6 joules of potential energy. At position 2 or so, right, 2 meters, it's all potential energy, it has no kinetic energy. And it'll never get above that point on the graph. It'll never go all the way to position 0. So these are going to change. Since we're limited to 5 joules, it says find the kinetic energy of the body at 4. Well, 4 has 0 potential, so it's got to be 5 joules. The maximum is all kinetic energy. Right? At 2, find the kinetic. At 7, it has 3 joules, so there are only 2 joules left for kinetic energy. And then 3, the kinetic energy at 9 meters It's only got one, so the rest is going to be kinetic, 4 joules. And then at 12 meters, it's 4 joules of potential, so it's 1 joule of kinetic energy. And then the speed, it says, will the body ever be found at 2 meters? Yes, it can be found at 2 meters, but it'll be at 2 meters with no kinetic energy. It'll all be in the form of potential energies. That's like reaching the high point, a ball thrown up into the air. That's not what this is, because this one, the amount of potential energy changes. There's some other forces going on here, right? Maybe some electromagnetic stuff. Okay, so now, example 3, we're given the position, the potential energy versus position graph for 2 kilogram body, but now we're limited to 3 joules. Right? And so the kinetic energy of the body at 4 meters, well, it's 0 joules of potential energy there, so that means all of it, 3 joules, is in the form of kinetic energy. At 7 meters, it's got 3 joules of potential energy. Since it has 3 joules of potential energy, it has 0 joules of kinetic energy. And then the kinetic energy at 9 meters, it's only 1 joule of potential energy, so we've got 2 joules there. And then it says, well, can the body ever get to 2 meters? Can it ever get to 12 meters? The answer for those two is no, not enough total energy. It only has enough energy in the system to get up to, on the graph at least, up to 3 joules of energy. Okay. So now we're talking about equilibrium. Equilibrium is a point where a particle does not move even for an instant. So, for example, like on this graph that you see here, if it was something like that, not quite. This is a point of equilibrium. If you put like a marble here or something like that, if you push it this way, it'll come back this way. If you push it that way, it'll come back this way, right? Also here, if you put a marble there, that's a point of equilibrium. Points of equilibrium are places where the slope is 0, where the tangent line has a slope of 0, where the derivative is 0. So that would be like that. If this is a horizontal line, it's also like that. Okay, and then this is stable equilibrium. Stable equilibrium is if you push it to the left or right, the force will push it back, right? It'll push it back to that position. Here, if you push it to the left or right, the force will then push it away from that position. And then, so stable, unstable, this is neutral. Neutral equilibrium, if we push it, the amount of force is not changing. The force pushing to the left or right is still 0. Because here, if I push this to the right, the force is going to be to the left. Why? Because this is going up, but the negative derivative is going to have a negative value, meaning the force will be pointing in the negative direction. If I push this to the left, right, it's sloping downward. Since it's sloping downward, the negative derivative is going to be positive. So if I push it this way, the force is in the positive direction. So it gets pushed back. That's kind of like this. Okay, this is a watch glass. Okay, and if I put this little marble in there, you can see the marble just stays put. That's stable equilibrium. Right? But if I turn it upside down, if I were to balance it perfectly and I had steadier hands, it would stay at that point. But then if I push it to the left or right, then it's going to continue going in that direction. So this is unstable equilibrium. This is stable equilibrium. And then if I just had a flat surface to put this on, that would be neutral equilibrium. Right? It works the same kind of way. So stability at equilibrium 1, we have an example here. This is, if we look at, from the previous example, calculus, relationships B, this is or something like this. Potential energy is a function of time. And then force, or not as time, sorry, as a function of position. And then force as a function of position. If this is the potential energy, what does the force graph look like? So this is going down, right? So that means it's going to have it's steep, so it's going to have a high. This is going down, so it's negative. A high positive value. And it goes to 0 here, so this is going to go through 0. But it's getting less steep as time goes on, so that means it's coming down. It's going to look something like this, right? Maybe not quite that steep. So what does that mean? As I go this way, the force is negative, right? The force is negative, which means that the force is in that direction. If I pull this thing this way, as it goes this way, that means the force is positive. At this position, the force is positive, but positive force pushes in the positive direction. So this would be an example here of a place of stable equilibrium. All right. If, though, I have something like this, potential energy versus position. So here's force is a function of position. The derivative of this would look something like this. If this is a quadratic, this is a cubed function. And you can see if I go this way a little bit, so this is 0, right? 0 slope, so that's right there. But if I go this way, then notice here that the force is positive. So if I go positive direction, the force is positive, so positive force means in that direction, this is going to be pushing that way. If I move a little bit to the left of the equilibrium position, then I'm getting to a negative force value. A negative force value means that the force is pushing to the left. So if I go this way, I get pushed further that way. If I go that way, it gets pushed further that way. That's unstable equilibrium. And then neutral equilibrium, again, would be something like this, right? Straight line across. So then what's the slope of that? The slope of that is just this, 0. So as I go this way or this way, there is no horizontal force pushing it one way or the other. Okay, so here's an example, example 4, and then that's it. Okay. So u of x is 8x squared minus x to the 4th. Okay, so we want to locate the equilibrium positions for this function, describe stability, graph the potential energy function, and graph force versus displacement. Let's try to do this all without a calculator. Okay, so since we have that, let's find the force function. And remember, force is the negative derivative, right? If you happen to forget, let's say you forget. First of all, remember that it's negative. I'm like, okay, to get the force, is that taking the derivative or taking the integral? If you're taking the integral, it's like multiplication. So if you multiply this, which is joules, by position, which is meters, joules times meters doesn't give us anything. But if I take joules and I divide by meters, and that's what derivation is, right? It's like dividing. Joules divided by meters gives me this. So, okay, it's negative du dx. That works. Joules over meters gives me newtons. That's what I'm going to use, right? So you can use the units even if you happen to forget. All right, so let's take a look at this. The derivative here is going to be 16x, negative 16x, plus 4x to the 3rd. Okay, what are the zeros of this? The places where this equals 0. Well, I can take out x squared, so then I end up with 8 minus x squared. Here I can factor out an x, so I end up with x. And I can do 4x squared minus 16. Oh, I can factor out a 4 as well, so 4x, x squared minus 4. So this is 4x, x plus 2, x minus 2. The places where I have equilibrium are the places where the slope is 0. So where's the slope 0? Where I have this, where this is 0. This is the slope. And so the places of equilibrium are going to be negative 2, 0, and 2. And now I need to figure out, are these stable or unstable equilibrium? All right. Well, let's graph this. And let's make a little table. So here's position. Let's do one for potential energy and a column for force. So we're just going to plug in our values. If I have negative 2 as x, I know this is 0, but what's negative 2 when I plug it in here? All right, so negative 2, this is going to be 8 minus 4 is 4. 4 times 4 is 16. Okay. Let's do negative 1. Go on that side. So if I put negative 1 into this, 8 minus 1 is 7. 7. So this is going to be 7. And if I put 1 into here, or negative 1 rather, negative 1, so this would be positive 16. 16 minus 4, this is going to be 12. Okay, if I put 0 in, then it's all 0. If I put 1 in, 1, this is going to be negative 16 plus force. This is going to be negative 12 for the force. For the potential energy, this is going to be 8 minus 1, so just 7 again. If I put in positive 2, this is a 0 for that one. And positive 2 put in here is going to be, oh no, that's that one. So 2 put in here, again 4 times 4, so it's going to be 16. What if I put in a 3? So I can see where this is going after 2. If I put in a 3, 3 squared is 9, but 8 minus 9 is negative 1. So this is negative 9. 3 into this, oh boy, 16 times 3 is going to be 30, 48, plus 27 times 4 is going to be 2, 108, so this is 60. Okay, so what do these graphs look like? Here's potential energy. It's all mostly positive, and then drops down, and then force versus position looks like that. So potential energy at negative 2, so negative 2, 1, 0, 2, 3, 1, 2, 1, 2, 3. So at negative 2, this is 16. And then at 1, it's at 7. And then 0. And then 7. And then 16 again. But then it's down at negative 9. Right, so like that. So it looks like it's doing something like this. Right. The force graph, I've got zeros here and here and here. And it goes positive, negative, positive. So it looks like it's doing this. Positive, negative, positive. Something like that. So these are the places of unstable equilibrium. This is stable. So stable equilibrium, unstable, there and there. So that's my answer. So we found the equilibrium positions, we described the stability, we graphed all the functions, and so that's it.